In this video, we will be discussing about the derivation and the law of mass action. Law of mass action is basically the uh, what do we say? It is the equilibrium law. What is equilibrium? Equilibrium Equilibrium is like the rate at which the forward reaction and the backward reaction both are equal. That is known as equilibrium. So here is I am presenting, like here I am telling you about the law, that is law of mass action. Equilibrium, and that is also known as equilibrium law. So what law of mass action state? It states that a rate at which a substance reacts is directly proportional. Means rate at which the substance react is directly proportional to its active masses. We will be discussing the what is active masses. The rate at which substance react. What does this means? This means that if the active masses, like the molar concentration of the active masses is high, like the amount of the active mass is high, so the speed of the chemical reaction will be fast. Means the molar concentration will be high, so the speed will be directly proportional, means the speed will be also high. This is what the law of mass action states. So what is active mass? Active mass is like the concentration in the cube dm mole cube, sorry, as I have stated here, the substance at which the rate is directly proportional to active mass. Now what is active mass? So active mass is basically the concentration in the dm mole cube. Okay, dm mole cube. Like if I would give you the example of the chlorine. Okay, here I'm taking the example of chlorine. So for example, I'm taking the 71 gram of chlorine, and the molecular mass of chlorine is like 35.5. If I'll divide with 71, so that will be 2 mole per dm cube. So this is what the active mass is known as. So the active mass is the mass that the concentration is the dm mole cube. Sorry, I have this written in the dm mole cube. The concentration of any substance in the dm mole cube, that is known as the active mass. What is like mole? 1 mole is equal to, and now if we talk about the 1 mole, so the 1 mole is equal to 6.1 into 10 to the power 23. 23. So this is what the active mass looks like. So as we have discussed the half statement of the active masses, the substance, the rate means the speed. Here the rate means the speed at which the substance react is directly proportional. Means the if the active mass of the substance will be high, so the speed of the substance will be more high. So this is what the first statement looks like. Now we'll be discussing the another statements, that is okay. So another is that the rate of the substance, the rate of the substance of the substance is directly proportional to the product, is directly proportional to the product of the active masses of the substance. Means here the product means the reactant. If you multiply the reactant with the product, so what the product will be coming out, that will be directly proportional to the to what to the active masses of the substance. So here again, if the active masses will be more, so the product concentration will be also more. Okay. Now if we see it by the uh, if we apply the law of mass action on the equation, so it occurs in the reversible reaction. I'm writing that here A, and plus here A is the substance, the reactant, B is also a reactant, the capital B is also a reactant. So when we are converting this, the reactant are being formed. So you will be getting to know that why we have placed double D and double C, double A, because the small D, or like the small letters, is for the coefficient. So this is what the statement. These are, as we know that these are what, these are reactants. When reactants are converted into products, and the products are again converted into reactant, that is known as reversible reaction. Like again and again products and reactants are being converted, so that are known as the reversible reaction. So again, what yes, now we know, like here it is like what A and B are the reactant, where A and B are, like here this A are the moles needed to balance a equation. Here this is what, this is the moles. Okay, moles, these are what, these are moles. I'm sorry, let me start from here. I don't know where it goes. Yes, here is, I'm writing mole, moles. This is what the concentration of the moles. Okay, this is mole. So now, like as it is directly proportional, so the rate of forward reaction according to the active mass. So here we will be like, what we will be placing, we will be placing the rate of forward reaction, means RF, rate of forward reaction, is directly proportional to is directly proportional to the active masses. So what is the, like we know that the active masses always be uh, considered, and it's the representation that is in the square bracket. So A means here the molar concentration, and the B we'll be placing B over here, and it's the molar concentration. Okay, so now as we have placed the reactant, okay, this A and B we have placed, now we will be placing the product, that is again, let me compare this first statement. So you know that whenever we end this proportionality sign, so we add over here the mm, constant. So RF means the rate of forward reaction. If we remove the proportionality sign, if we remove this proportionality sign, so we add the constant K, that is the equilibrium constant K, and Kf. For Kf, why? Because this is the forward reaction, so I will be placing Kf. Now A, again the same, the molar concentration, that is always in the square bracket. Small a means the molar concentration, small a consider here, B, small b, that is the molar concentration. So this is for the rate of reaction, the forward reaction. Now we will be looking forward at the rate of the reverse reaction. So R is directly proportional to the active masses C D, then the molar concentration, this and this C, and that A and that B are for the molar concentration. Consider like they shows the molar concentration. Okay, so now R, and if we remove this proportionality sign, so what do we add? We add K R, because it shows here, it is what it shows the rate of reverse reaction. So that is C, molar concentration of C. Now D, molar concentration of D. Okay, so now here both RF and R are equal over here, because at that is like as I told you that at one state both forward reaction and backward reaction achieve the equilibrium. So here they are achieving the equilibrium, that is the rate of forward reaction is equal to the rate of reverse reaction. Okay, so now means you can also say Kf is equal to Kr, we can also say. So like here now we will be placing always at the upper side the reactant. What is now Kc? Kc is what, when these two will be combining, the new, like the equilibrium constant will be coming, and that is Kc. We'll be discussing Kc, like it is the equilibrium constant. What it is? It was the unit, equilibrium unit. But must notice, but it is the must thing that equilibrium constant is not but sometime equilibrium constant have unit and sometime it do not have a unit. So don't consider Kc as the proper unit, just is for the representation here. So Kc, now we will be placing C D divided by reactant. A was the reactant, and again B was the reactant. So you can also write, Kc is equal to Kf and Kr, or you can also write Kc is equal to product divided by reactant. This was the derivation of the Kc. I hope that is clear. Okay, here Here it is the derivation of the Kc. So hence it is proved that where Kc is called the equilibrium constant. Hence it is proved that the laws of action describe the relationship between the active masses of the reactant, this reactant, and of the product. So all the reversible reaction can be expressed in this. Okay, all the reversible reaction can be expressed in this. So here I'm giving you the example how we can express the reversible reaction. For example, there is 2SO2 reversible reaction, O plus oxygen plus 2SO3. So this was C and this was D and this was this is what, this is AB. Okay, consider that. So as we have discussed that always C and D will be coming opposite upside. So Kc is equal to what? First of all, let us write that what is Kr and what is the Rf and what is Rr. So Rf is Kf. What is Kf? What is the forward reaction? This is the forward reaction. Okay, we'll be writing this. That is CO2. Okay, let me, and CO2 and this 2 CO2, that 2 will be upside. Oh, sorry, I've just written the wrong one. Wait, let me write. I was just so confused over here. So let me write it again. I'm so sorry for that. Like here, C 2SO2, here 2 plus oxygen 2, that is like the reversible reaction. Now I'm writing the correct statement. I was so confused over that. So that is like here the sulfur dioxide, this is the sulfur dioxide plus oxygen to form the sulfur trioxide. Okay, sulfur dioxide plus oxygen form the sulfur trioxide. Okay, so this is what, this is the forward reaction, and this is the reverse reaction. Okay, we know that this is the reactant and this is the product. So let me write that Rf is equal to Kf, and that is what, that is let us write the active mass in the curly bracket, CSO2. This is what, as we know that this is A, small a, and this is what, this is the capital A. So here, as we have discussed that always the capital A, the molar concentration will be at the upper side of the curly bracket, square bracket, sorry. So here what is that, that is 2. Okay, plus, we'll be not writing plus here, O2. So as O2 do not have any do not have anything. So now as we have placed the reactant, so let us write that what is R. Okay, it is R, that is equal to Kr. The what is, yes, here. Okay, here it is. Now as we have the C, we have the small value, so we'll be placing at the upper side S, SO3, but the constant of it will be placing at the upper, as we the molar concentration is always at the upper side. So Kc, now again Kc is equal to, as we know that R is always at the upper side, so SO3 now 2. Now I'll be placing the reactant, as we know that the product is like here is the product, here is the product, so here product is always what, always at the upper side. We have discussed in our our what, our derivation, the product is here, so we'll be placing the product. We have placed our product. Now after the product we have a reactant. So what was the reactant? Here reactant is here, we RF, we'll be placing RF now. So SO2 O2 sorry. So here this is what, this is like the Kc of the, like the expression of the Kc constant. Okay,